I have just gone over the TweakyWee. Here it is. If you want to hear the full conversation on the TweakyWee, you can check first hours. All right, here we go. So the question on the table is, do an impulse momentum theorem problem. What now?
Just like with the force and the time.
Sure, I'll do you one better. Have you gotten to the Jello problem yet? How do you feel about the Jello problem?
I heard Lily talking about it, and I'm afraid.
Great. Okay. It's not that bad. You've done a problem that's very similar about it before, but this is a good thing to go over, especially right now. So earlier in the homework, you did a problem with a car, and it told you the resistive force, I think, on the car. It told you a bunch of stuff about its momentum. I don't want to get into the numbers because I think you can do that on your own, and that's relatively easy. I want to focus on the concepts. So what I said was, I told you what force friction was. I'm going to make up numbers for this particular example, so they're just very, very, very easy. Okay? I think I told you that force friction was that, and I wanted to know what force engine was. Okay? Now, previously on loss. All right. Most of the problems, what I did is I just told you the net force. I would say something like, hey, the net force is this way, and I would say it's like 200 newtons. What would that tell you?
That the engine has a force of 200.
Not quite.
Oh, wait.
If I said it like this, I did not say the engine has a force of 200.
That's the net force, so it's like 200 greater than the friction.
Agreed to both of those things. So the engine has a greater force of force friction. What do you expect the object to now do? Specifically, it's going to accelerate that way. If you make some general assumptions on the fact that it's either stopped or already going that way, you could say it's going to speed up, which is exactly, I mean, technically, if it was going the other way, it would slow down. Not what I'm worrying about right now. Okay? So in this case, let me go to a different spot. Actually, no. If I were dealing with it as a net force, this is all there is. But this is not actually what you're used to from previous chapters. In previous chapters, I regularly spent a lot of time working on the individual forces. So we would do something like force of gravity and force of normal. And then we would ignore force gravity and force normal. Why?
No work.
What do you mean they cancel out?
They're equal and opposite.
Remember that this is just, vector addition, they're equal and opposite. So what you would typically do is you'd say sum of forces, and we would handle this actually by saying there is no acceleration, which technically made that sum of force is 0. Now what that means in terms of vector addition is this. You take four vectors, just making up some at random here, not actual ones. Boom, 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 and boom. And it arrives back at the 0. Now, that's kind of complicated, so what we decided to do is let's not worry about it all at once and just worry about the y and the x individually split up. So here you'd say they cancel each other out because one goes up, the other goes down, so you usually draw it from there, but the vector addition technically is that right there. Yes? Okay. Now that being said, what happens in the x-axis? Well, exactly what you've already said. Force friction is here. Force engine is bigger here. Now, you can do this math pretty easily on your own because I've made the numbers pretty nice. If friction is 1,000, and that's going to be the case, how much is force engine? 1,200. Pretty easy. Did that in your head. No problem whatsoever. But what really is happening is a vector addition between these two right here. Why is that 1,200? Because this, I'm going to highlight in yellow real quick here, this is that part of the vector, right? This here is, I'm sorry, my arrows are not to scale. This is 1,000, so this has to be 1,000 over here plus the extra. It's extra that causes it to accelerate. Yes? So, in one of these problems, like the Jello problem, okay, the only difference is simply this. Usually, what you do is you just take this 200 and plug it straight in there. Yes? But that's not what you would have done over here. Over here, if I was looking at the x, you would do the stuff we always did. And the first thing you do is it going to accelerate? And you'd say yes, right? Okay? And what would you do with this part right here? You plug in the individuals, right? You do exactly, you'd say force engine minus force friction. And what you're doing is you're saying, hey, this force engine minus force friction is exactly the same as this right here, right? So what you did is, rather than deal with the total, you simply plug in the individuals. And what I would do here is, instead of using the total, I plug in the individuals. Yes? And if you do the math all the way out here, the algebra, I would divide by time. And I'd usually be left with, I'm going to kind of do this a little bit quick here. I would usually be left with this right here. The difference is equal to that. This is just the total. It's the 200. So what is the math going to tell you? Well, what are you going to do to get force engine by itself?
Add the force friction on the other side.
So what does this math essentially say? It's what you very quickly did in your head a second ago. Hey, how much is the extra equal to, guys? 200. How much is force friction equal to? 1,000. So what does force engine have to be? 1,200, right? That's all that's technically going on. So simplistically put here, if you want kind of just the nuts and bolts, if you're dealing with a net force, you just plug the net force in there, easy peasy, right? If you have to deal with individual forces, you simply just plug the individual forces in for net force like we have always done. Now, one other thing to highlight specifically in that Jello example, so if you haven't seen it yet, somebody jumps off into a vat of Jello, is do be careful that you split up. The impulse momentum theorem works, but it's not like an entire problem type equation. The impulse momentum theorem can only be used to describe a section when the net force stays the same. So you can't use the impulse momentum theorem to go all the way from here to here, because what changes? Do the force diagram quickly in your head. It's super quick. Okay, what's the force diagram up here? Push gravity down, and that's it.
And then it's also
right?
Force.
Not while he's falling.
I meant like the next, when the last arrow.
In the last arrow here, what do you got?
The Jello.
So it'd be force of gravity, and?
Force is normal, but like on every side.
But we were going to say Jello.
Yeah.
You probably want to say Jello instead. And is it bigger, equal, or less than force gravity? Why bigger?
Like isn't it like everywhere though? Like are we in the Jello?
You're falling into the Jello.
Are we,
Sure,
like,
but if you're falling into Jello, yes, it's pushing you this way, but what are these two going to do to each other? Cancel each other out. So the only one that really matters is the one that's pushing you up. So why should Jello be bigger than gravity? Just basic kinematics here. That says the acceleration is going to go which way? Up. Why does it make sense that the acceleration, what do you expect to do in Jello? Slow down. So if your velocity is that way, which way does acceleration have to be to slow you down? Has to be up. Make sense? The other thing to be careful of here is initials and finals. I would just use kinematics on the top. Why? Because you just said a second ago it's just force of gravity, so you know what the acceleration is. Obviously, you'd make that the initial and that the final, right? Would you even worry about impulse momentum theorem on the top? No. Then, when you take over impulse momentum theorem, don't forget that this breaks down into this. And while I said it was the final, that's the final for the top. This is when it's hitting Jello. So this final for the top is now the initial for the collision. Does that make sense? Also be careful with your signs. More than likely, most of you are going to say up is positive. So what should velocity final be here when it lands? Negative, if you've done it correctly. To show that, here is the momentum. Here is the momentum initial when it hits right there. And what do you expect the person to do in Jello? Slow down to a stop, which would mean what simplification here? What's that? Momentum final should be 0. Be careful not to cancel the wrong one. Why does it matter? That little negative right here. Why does the negative matter? Well, this is the change in momentum. If you have a negative momentum initial going down, in which way does it need to change to go back to 0? That needs to be its change right there, right? If you say that change is negative, that's going to make things real wonky real fast, because what you're saying technically that's happening there is, hey, when I hit the Jello, I was going this speed, and then I changed my momentum in the negative direction. What does that mean you should do after hitting Jello? Be going faster. That Jello has accelerated you, has propelled you forward at a particular speed. Does that help or answer the questions that you initially had?
Yes. I have one more thing.
Go ahead.
This real quick. On a momentum diagram that's 2D, do you have to do a before and after? Because
Yes.
I don't.
Every single momentum diagram needs a before and after.
Because like.
Do you want me to do momentum diagrams?
Yes.
So, okay. Well, there's a bunch of questions. Are there any questions continuing on this conversation right here? Let me actually go back and put up the right answer, so I'm not left with the wrong answer up here and just asking people to remember that.
I did a diagram. I don't even know before or after. I know that it's a diagram of something.
True.
What happened?
Okay. Let's get a handle. Are there other questions, just so I can kind of like parse this out and try to go, try to put this in an organized fashion as opposed to just kind of randomly go, what else you got?
In real life, is momentum always conserved?
Yes. Now, the thing that it will make it appear not conserved is not tracking momentums that are actually in the situation. For example, in our lab, one thing that we, for the most part, don't worry about that does mess with things a little bit is, let's say your momentum runs in, let's say your object runs into the track. Technically, there should be a momentum of the track. That should change things, which will mess with your particular amount of results. So that would make momentum not conserved. But in actuality, if you were to track absolutely every single object in the situation, momentum is conserved. Okay, I'm going to go ahead and guess that somebody wants me to talk about the lab. Yes, no? Because based on the number of emails I've gotten on it. And some people have. It kind of depends. We'll talk about why struggle or not. If you and I'll go over it that way. You can be like, oh yeah, I didn't have that issue, and give you that confidence there. Any other questions? You have a question over here, I thought?
Yeah, I did. I'm
Go
still
there next.
confused on like why momentum isn't a way to describe motion. Like,
Oh, excellent question. Excellent. It is. It certainly is. I think it's not a new way because that is just Newton's second, and that is just Newton's third. So really, if I was to put these into like an actual chapter and it make the most sense, momentum is kind of a, you know how they take like a chapter and they give it like subsections, right? Momentum is really a subsection of this particular chapter. If you remember back to the forces chapter, our brains were not at a spot to accept a lot more of this amount of weight. So I think that I put it, momentum's kind of a mini chapter. It's a half chapter because it's not new. It's just an extension of that, but I don't want to make chapter 4's test just so bloated and ridiculous that you come in here for an hour and you're just like, I have no idea. Right? I like you to be more comfortable with energy as well as with forces before having this conversation, but it's really just an extension of the forces chapter. Does that make sense?
Yeah.
Okay.
For the worksheet,
Sorry, I didn't. Go ahead.
there was it was like the one with the 4 questions, like hard hitting, the one where you get pushed.
I don't remember right off the top of my head, but
Just
which one is on?
the number. I
Which assignment is it on?
6.5, I think he's talking.
Is it is the penguin shoving me?
Yeah, you just want to draw the momentum diagram of the whole thing.
This one right here at the end. Yeah.
That could be the momentum diagram.
Sorry, go ahead.
For a lot of questions, you just ask about the total momentum. You have to draw a before and after picture.
Yes, 100%. Even when it's pretty easy. I'll show you when I talk about momentum diagrams, like really easy ones and what they should look like, and more complicated ones and what they should look like. Maybe.
Yeah, I was wondering if you could like walk through all those problems and then walk through like what's required for the test and stuff. Like
I don't know if I'm gonna have the full time to be able to go over like all of that, and that's kind of what I was attempting to do yesterday. That being said, before I forget, I am gonna do kind of a mini tutoring session after school today if anybody has time. If you don't have time, which I fully recognize because it's kind of a little bit last minute, shoot me an email on the picture and I will try to do my best to show that, but I'll try to do that with the momentum diagrams here in just a second as best as I possibly can. The tutoring session is not going to be just come in and just kind of like goof off. It's going to be specifically for people to come in with specific questions so I can tackle them pretty quickly. I don't think we'll be here the full hour.
So how do I know which way to draw the final, like the after the collision?
It tells you what the velocity of Spainhour is after the collision.
Like the questions above.
Doesn't this look like a
What do you mean?
diagram that you just
The questions above, it doesn't tell you the final.
and
It just tells
apparently
you
that's not before and after.
beforehand.
The reason why is because the questions above are much simpler in that the questions above are perfectly inelastic. So you don't need to know about any individuals afterwards because the total. Let me clear it up in just a second. All right. So let's begin with momentum diagrams. Let's start off very, very simple here. Okay, so we're all on the same page. I'm going to start off looking at an example of a cue ball hitting an 8-ball. Things that are made simpler here is the fact that they have the same mass. Okay, and we're going to start off with the 8 balls not moving. So I hit the cue ball, so I'm drawing the velocity right here, into an 8 ball that is not moving. Okay, here's the momentum diagram in what you draw. What you draw is you draw the momentum of cue ball initial, and to represent the 8 ball, you just put a dot. So I've drawn the individuals. Okay, after drawing the individual, I draw the total, which is just a sketch, but pretty easy. Underneath that, what's the total going to be? Same as the cue ball, because you're just adding a arrow to nothing at all, right? Then, you don't have this capability to know on your paper, but roughly speaking, attempt to draw the exact same arrow. Because conservation of momentum says the total initial should equal the total final. Now, if this was an elastic collision, what would you expect the cue ball to do? Probably stop. And therefore, in order to conserve this, the momentum of the 8 ball should be the exact same, which you see rectified on a flow table by the fact that you hit the 8 ball, you expect the cue ball, you expect the cue ball to stop, the 8 ball to take off at the same speed. Yes? Let's make it a little bit more complicated though. Instead of a cue ball and an 8 ball, let's imagine that the first object is Spainhour running as fast as possible, and the second object is a sumo wrestler that is going to hit, and he's going to be elastic collision as well. So here we go. We have Spainhour. Actually, Spainhour and sumo is not going to work. So let's go teacher. Okay. So we have the momentum of teacher initial. Okay. And then the sumo wrestler over here is not going to be moving. So there it is. Move you out of the way. Should be about the same as the final. What do you expect Spainhour to do upon colliding with a person that is roughly twice his mass? You probably expect it to bounce back, right? This is where things start to get a little bit interesting. Let's actually move you over here so it's a little bit more obvious. Over with the initials. So you'd expect Spainhour to bounce back a little bit. Or the teacher. Final, dummy. So teacher initial, moving to the right, not moving. So that means what must the sumo wrestler have in the terms of their momentum? I go from the end of this right here. Weirdly, the momentum of the sumo wrestler is larger to the right than Spainhour's was to the right. Now, will that mean the sumo wrestler's traveling crazy fast? No, because twice the mass. Did I double the velocity here? Sorry, did I double the momentum of the sumo wrestler relative to what I was? No. So since he has twice the mass, he's not going to be going the same speed as Spainauer at the very end. How are we doing here? To begin with.
I mean, look at the screen.
Weird. Oh yeah, that happens. I can do that. Where's the? I pressed that button. There it is.
Can we do 2D?
Yeah, and that's next. How do we feel about this so far? Okay. Now, the way I'm going to change this, and the reason I started here was this. Let's go back to my cue ball and 8-ball example. And we're going to start the exact same way. So I have the momentum of cue ball initial and the momentum of 8-ball final. And there's the total, roughly drawn the same arrow. And there's the final. Okay, everybody's good. The only major difference I'm going to change now is this. We'll take the 8-ball and just position it a little bit higher, such that the cue ball strikes not dead on, but right here. Let's first talk Newton's third law. Newton's third law, because they collide right there, would cause a force of cue ball on 8-ball, right? And then what does Newton's third law will also say is happening? There's going to be a force of 8-ball on cue ball. I'm going to break this down a little bit more technically than I expect you to. As a matter of fact, before I do the technical thing, just tell me what you expect to happen with this 8-ball. If the cue ball comes in and hits underneath the 8-ball, what do you expect the 8-ball to do? Like, in what quadrant do you expect it to go? Up into the first. What do you expect the 8-ball to do afterwards? Probably down into what quadrant? Third. Probably down into the fourth. In other words, you'd expect the ball to get hit like this guy to go that way, and that guy to go that way. Yes, is that fair? Is that reasonable? Okay, so let's see what happens here. Number one, if I break this down into technicality, let's look at force causing acceleration. So acceleration is going down this way. If I split it up into its components, I have a velocity going in the positive x, and my acceleration going in the negative x. So what do I expect the velocity vector in the x to do? Get smaller. Since there is an acceleration downward and there is no velocity anywhere on the y, which way do I expect the cue ball to go? Down. So in other words, it should have a little bit smaller in the x and it should have some in the y. Yes? So I'm going to pick a different color here. So what I said was a little smaller in the x and some in the y. Here is the momentum of the cue ball final going down into the fourth quadrant like we said. And which way do you expect the 8-ball to go? Up into the first. Now what people struggle with here is this. I'm going to do this in two perspectives. The first which is just a basic vector addition. What vector addition says is those two have to add to this, and the two individuals here have to add to this. Now what's weird about that for most people is that's not how you envision it. How you envision it is this. Are those exactly the same thing? Yes. I didn't draw the arrow perfectly here, but
So is that triangle you're after?
yep.
And then you're
So look, those two vectors add to get the final. So that's the way those are going to go at the very end. Does that make sense? So what you should have rectified here is this. To show this visual representation with numbers, here's what we've been doing. Here's what I just said. I said, if I take both individuals and add them, I get a total. Those two totals have to equal each other. And these two individuals have to add to also get that total right there. Do we see that? Trent? Hello, sir. How are we today? Good. What's your name? Jeffrey. Jeffrey. Andrew. Nice to meet you, Jeffrey. Let me get your money real quick. There's a question. Yes, Bob. Sure. Go ahead.
Project your voice.
I got you.
Okay. Do you have to draw them both from the start point, or can you like make it like
Have a good one.
can you make it end like you do it the first time? Like when you draw the final, you have to draw them both from the start.
I would not. No, 100% I would not. I just drew it like that because I felt like that's what most people see it. I would highly suggest what you draw is exactly what I did the first time. Just show these two arrows the same and show those two arrows right there adding. Again, I only showed that real quick because that's sometimes people's hang up. Like, why is the 8-ball, why did it teleport over here before it began going in that direction? No, it's not what we're saying. We're saying it has to go to combine these two momentums to get the same as the original, but it makes sense kind of that they would leave from the same spot. So I would suggest you draw it like that.
So
Yeah.
the purple arrow is the same, like the momentum.
Total momentum final
Yeah,
or initial.
the total momentum final. It should be the same size as like the other ones, even though
Correct.
they're like in like.
These two must be equal.
Yeah.
Okay, let me just do number 4, the penguin and Spainhour example. I'll at least do the momentum diagram for you to kind of get a sense of at least A and B. Okay, now you do not have to do it both ways, but I kind of suggest this. Like if two objects are going to collide like this at the very beginning, I would suggest drawing 2 pictures. One, to give you a mental picture of kind of how they're going to collide, and 2, their actual momentum combination right here. So here shows you what's going to happen, and you can kind of get a sense of like, you know, in your imagination what's going to occur, but this is the actual momentum diagram. This right here, let's see which way am I guessing they're going to go. That's about the same velocity, so I said that one has more mass.
Like once you do the initial and they're both moving.
Not with your numbers. I'm making up numbers right here because there's a lot of possible options. The possible options depend. The possible options depend on where it collides. Like the difference between this example and this example was simply where it collided. This example collided because it hit right there, and so my force is force of Q on 8-ball, force of 8-ball on Q ball, right? It's right here in the X. It only changes things in the X, right? This was weird because it hit underneath to go in that direction. So the reason why there's not, let me show you the penguin example to give you an idea of like why there is a very particular answer. So what you heard me saying just here is possible options, because there are a lot of possible options depending on where they could possibly hit. I was just trying to get a good sense of a realistic one that you would expect to happen in this case. Well, let's do the penguin example. So what we have here is Spainhour traveling down initially, and there is a penguin standing there, so just standing there. Okay, I'm going to draw this vertically as opposed to side by side because I think it makes the most sense. So I've drawn the initials. So the total is just that right there. Cool being so far. Yeah. Then I try to draw that arrow about the exact same size and fail miserably due to my unrealistic artistic talents. Now, the reason why there's a very specific example is what it says is it tells you the velocity of Spainhour afterwards. It says Spainhour is traveling faster than he originally was. I think it goes 6 and up to like 7 and change or something like that, which means the arrow is technically longer, okay? And it says that he's going at 253 degrees, meaning instead of straight down at 270, Spainhour's new vector should be here-ish. In what direction did the penguin have to stand? And how did he push Spainhour that he would cause him to go faster and in that direction? So like in this case, like if I was walking down the hall this way, where would the penguin have to go? The penguin would have to be behind me, shoving me forward in about that direction. Does that make sense? So if the penguin was standing still and shoved me like that, where would you expect the penguin to then go?
The opposite way.
Back the opposite way. So we expect then that the penguin, since it shoved me down this way, should end up back here in the first quadrant. Does that make sense? And if you do look at the momentum diagram, in order to conserve, we know the final has to be equal to the initial. Those are definitely not the same. Spain-Hour sped up, and therefore the momentum of penguin final has to be back in the first. Now, exactly what angle in the first? Yes, there is certainly open to interpretation there. That is not what I am worrying about when you draw your diagrams. I'm not going to check yours and I expect 60 and you got it at 30 and I'm going to spend a lot of time and effort kind of being like, this is not right. No, I'm expecting like you to be able to get the general gist of what I just said. You should get that Spain-Hour was going faster, and so the arrow should be longer at 253, okay? And therefore this picture does have certain expectations, but not exact size or exact angles. Does that make sense? So that what I just drew is the answer to A on that problem. B, which talks about the force diagram, goes to what I just said a second ago.
That would be required on the test.
Probably, yes. But just here's all it is. Hey, I expect a force of penguin on Spain-Hour back down this way. Why do I expect that? Because Spain-Hour sped up and was traveling left. And if there is a force on Spain-Hour that way, what must there also be?
Other thing
The-
on the other one.
Yep, the force of Spain-Hour back on penguin the opposite way. Does that make sense? If you understand these diagrams, it is so much easier to understand the math. For example, in this case right here, okay, here's what's going to happen. This arrow is this arrow is this arrow, right? Because this plus 0 is just this is this, so all three of those are technically the same size, even though they're different vectors. Make sense? So then the question on the math is simply, how do I figure out this vector right here? I would start with the equation like I did on Friday, right here. The momentum of Spain-Hour initial plus the momentum of penguin initial equals the momentum of Spain-Hour final plus the momentum of penguin final. That being 0 because he's not moving. So how do you figure out this? Just a little bit of algebra. Keep in mind when you do the algebra here, since these are vectors, this is vector addition, not regular addition. So how do I subtract a vector? You add a negative, right? So how do I do this? What that says is to get this, I take Spain-Hour initial, right here, and subtract Spain-Hour final. Is that going to give you the same as that? It should. More questions?
I'm sorry.
Let's go here first, then we'll go to Trent.
On the first problem of the homework, we don't calculate velocity final or like anything final. We just do the total. So then,
I don't remember exactly
Well,
what that's, but very possibly.
so would we just like do what you just did here and then just like?
So it's even easier on 1, 2, and 3. The reason 1, 2, and 3, well, yeah, I mean, this is just practice vector addition. This is just straight up vector addition. 110% vector addition. That's all it is.
Because I got my initial triangle. Well, I got a triangle, and it's a good triangle, but I don't know what the triangle is. But I have.
So that is 2700 at 152, so you should have it somewhere over here. Okay, and then you should have a smaller arrow because it's 18 at 252, so right down here-ish. So I would say that's probably about right. I don't know if it I can't remember if it ends in the second quadrant or the third, but roughly
Yeah,
this is.
what I have.
Yeah.
And that's my initial triangle.
Well, it doesn't really matter because this is just vector addition. This
Oh, okay.
is just
So I
vector.
couldn't.
Again,
I couldn't
number
have
one
a
is
triangle.
just vector addition. There's no such thing as two triangles. There's no collision here. There's
Yeah.
no collision here. It's just a vector addition. Now,
Yeah.
2 and 3. you got a wide receiver colliding with a linebacker and a Blues defenseman colliding with a Blackhawks player. The reason why these are way easier is because they're inelastic collisions. So in an inelastic collision, there is only one momentum final, right? Because it becomes one object. So if I just let's not make something up. Let's use this. So we have the wide receiver going at 180 degrees. So this would be the momentum of wide receiver initial, okay? And then you have the linebacker that's going to collide going 20 degrees. So they're going to collide. I would draw it, like I said, this way first. Here's the momentum of linebacker initial. And then I would draw your vector addition. Here's momentum of wide receiver initial plus the momentum of linebacker initial. So that's, and I don't know the exact amounts. So that's the total initial, right? What's the total final? The exact same as that.
Okay.
And why is there no reason to split them up?
Because it's inelastic.
Because it's perfectly inelastic. That's it. They aren't split up. They are one object. If you want to draw it, I mean, I guess you could draw the exact same vector again and say total final, but those two mean the exact same thing. So why draw it another time? They're not separate individual at the end. So that's why you don't see them separately like you do in the elastic collision. So the simple thing in that case is you don't have to do any negative vector addition. It's just this. All that math says is this. The momentum of linebacker initial plus the momentum of wide receiver initial is equal to the total momentum final. Yes? Since that's only one vector, just do normal vector addition between the two of them. That's this. And if you want to know the final velocity, what's the only thing you got to do? Specifically what math? That's very vague. I feel like if I ever gave you that answer in here, like if you looked at me concerned and struggling about momentum and say, Spano, I'm just exacerbated. I am full of emotion. How do you do two-dimensional kinematics and momentum? And I looked at you and I just said, math. I think you should show me a finger. And I think that all of them are viable in this situation, rightfully so. Anyway, what do you do? Divide by the mass total, which would be the combination of both of them, but yes. Other questions? I'm on to the lab here. The little remaining amount of time I got left. So the main thing about the lab is this. I have gotten good results. I believe that the makeup data does have good results. I've also had people like legitimately doing the lab pretty well and make mistakes. Your biggest mistake, not mistake, error. Okay, have error that make the results not seem correct. Let me give you, for instance, to show you where the problem arises. Let's say, for example, that elastic collision, the very first elastic collision in which the car comes in, hits the second car. This second car takes off pretty fast, a little bit slower than that one, and so this guy right here should still be moving with a little bit of momentum because that didn't take the full momentum over there. This thing over here is moving incredibly slow because of that, because it doesn't have a lot of momentum. Now the problem with that, since it's moving so slow, you need it to be a constant velocity and your gate is over here, so you have to wait. You have to wait. You have to wait. You have to wait. The problem with waiting is as you're waiting, what is potentially happening to that cart? Friction could potentially be slowing it down, or you might have had a lab table that's a little bit angled, and so possibly it actually has a little bit of a slope, making it go a little faster than it's supposed to be, actually speeding it up in that case. Ideally, it's constant, but we can't confirm that 100%. So you're not going to get exact. Ideally, the whole purpose of the lab was to show this. These two numbers should be pretty darn close. That being said, like I said, I got good results with my makeup data online, but I've seen people do this job pretty well and not be off, and be a little bit off. So if your numbers aren't matching up, there's one spot I would say be careful with, and that is the last example of elastic. And the reason the last example of elastic is particularly important is the first thing that ran into the bigger object bounced back the opposite direction, which means its velocity better be negative. If you haven't taken account for that negative, that would certainly mess up your results pretty considerably. Beyond that one, the numbers should pretty close to match up. So I would suggest, and sometimes numbers seem way more off than they actually are. I would suggest looking at percent error. Okay, Percent error is just which one you like. Actual minus expected divided by expected times 100. But that math, real quick, is this: if I expect 8 and I get 10, how much am I off? 2. 2 is what's called error, just natural error. That's all there is. Now, do you care whether or not you're off by 2 on the top side or the bottom side? If that was 10 or 6, no, you're still off by 2. Who the heck cares? Right? That's why you regularly see this in the equation. Actual minus expected, and then there's an absolute value. That is calculating the error. How much is it off? That's all it is. How much is it off? Now, the weird thing here is this. You want to say, which one's the expected and which one's the actual? There are labs, such as this one, where you don't necessarily know which one is the right one because one is not necessarily better. I would say that probably initial has less likelihood of being off because there's less stuff that's happened to it. So I would probably make my initial the expected, but who the heck cares? Okay. Then if I'm off by 2, but the scale is 0 to 1, is that a big deal? Yeah, that's 200%. That's a big deal. If I'm off by 2 and the scale is 0 to 100 to 10, is that less of a deal? It's less of a deal. Still 20%. Seems like a decent deal. Okay. If I'm going off by 2 and off by a scale of 1 to 100, now we're at 2%. Now we're starting to get this seems pretty darn good. So that's why we give it scale. How do we give it scale? We simply divide on the scale that we are on. How do we decide what scale we're on? That's where we use the expected. So in other words, we're off by 2 right here. How much is 2 compared to 8? 25%. Does that make sense? So use percent error to talk about how much potentially you're off and whether or not this confirms things. And if it doesn't confirm things, you can talk about why. On a lab, some people spend a lot of time freaking out, because my numbers don't match, my numbers don't match, my numbers don't match. But that's labs. Like, labs sometimes don't have conclusive results. You don't, what I'm looking at when I grade your lab is not, did the lab do exactly what we expected to do? Because if you go work in a lab someday, that's usually not going to happen, okay? You are not going to regularly be in a lab and my results always do exactly what I expect them to do. No, they don't. 90% of the time, they're not going to. So what I'm looking at in the lab is, how do you handle that? How are you tackling that? How are you talking about that correctly? Okay, talk about what could have gone wrong. Understand what could have gone wrong. Okay, any other questions? I wouldn't spend too much time in the lab freaking out about that type of thing. If you answered the lab questions, the main purpose of the lab was to practice lab momentum diagrams. Okay, practice momentum diagrams, have that conversation about kinetic energy that we did, and do some of the math on number 3. Actually, I think that was 3 and 4. So, yeah.
Do we not need, like,
You had to do all the things that it said on that paper, is what you had to do.
I was meant to write it down, but
Right here, make sure you do these things. 1, momentum diagrams. 2, calculate in the first elastic collision, was kinetic energy conserved? It won't perfectly be, but it should be close. And finally, a data analysis, writing a paragraph that confirms, is conservation of momentum. This is where you talk about good results versus bad results.